Hello, my name is Sinjin Dixon-Warren. I work for TechInsights in Ottawa, where I am presently the SME for power electronics. Today, I will be talking about GaN technology in USB adapters. First, a bit about TechInsights. TechInsights exists to support a fair marketplace where semiconductor and electronics intellectual property can be innovated and monetized. By revealing the innovations others cannot see inside advanced technology products, we prove patent value, drive the best intellectual property and technology investment decisions, and provide in-depth supply chain and purchasing analysis. AC adapters are ubiquitous in the modern world, since the mobile devices we love need to regularly attach to grid power for charging. The first truly high volume application for GaN technology is likely to be USB chargers for mobile devices. TechInsights has been actively monitoring this market, and you can see various blogs and articles we published, but we're not the only people, as can be seen from the quotes on this page. In 2019, the market for wall chargers is estimated to be $1.3 billion. So why would one want to put GaN in a USB-C charger? There's a number of reasons. First of all, more powerful chargers, smaller form factor. The goal is 20 watts per cubic inch. Higher efficiency. The goal is greater than 95%. Basically, the power supplies typically use active clamp flyback converter technology, where GaN provides a number of advantages, specifically lower RDS(on), higher breakdown voltage, better reverse recovery loss, lower switching losses, and higher frequency. Bottom line, switching to a GaN from silicon can cut the size of the charger by about 50% with increased efficiency. So what we're going to do in this presentation is just survey some of the chargers that TechInsights has analyzed in our teardown lab and in our other labs, and give you just a flavor of the evolution of this market. We'll begin with what I call a false start. So in 2015, TechInsights procured the Aukey Zolt USB charger. Aukey was claiming to be a bulk GaN technology company. However, when we opened up this charger, we found that it was actually based on silicon carbide power FET technology, and that the die was likely from Cree. The first true GaN-based charger that TechInsights has identified and analyzed was the RAV Power RP PC104W device, which is a 45 watt USB-C charger. We procured these chargers in December 2018, and we found that they were based on a Navitas reference design. We also had a look at the Made in Mind Mu1 international charger, and it had this identical design. The device contains two Navitas NV6115 GaN power ICs, shown in the upper left here. The next generation Navitas device that we found in the market was the Aukey PAU50, and I'm going to talk a little bit more about this device because there's a little twist that we'd like to talk about. And it was a 24 watt dual port USB charger, which we procured in March 2019. And it contains, this time, the Navitas NV6252, which is an integrated GaN half-bridge device, where there are two GaN dies in the single package, shown up here in the X-ray at the left. I could talk a little bit about GaN technology, Navitas technology, which TechInsights has analyzed in considerable detail. So here's a higher resolution picture of the X-ray with the photographs of the die overlaid on the X-ray. The die is being deprocessed to the gate level, and although you can't really see it in the layout here, we have annotated the block layout of the die. The key thing about Navitas technology is their integration of analog transistors and a power transistor into the same die. You can see the device contained two dies. So just a little bit more about Navitas technology, which we've analyzed in considerable detail. They're fabricated by TSMC, and they use very elaborate GaN on silicon epitaxy with 10 plus layers and two superlattice layers. The superlattice layers serve to improve the quality of the final epitaxial GaN and also increase the breakdown voltage of the device. Here we show an overall structure of the transistor structure, and here a detailed TEM image showing the GaN-based mesa, which is used to form the gate. This is a normally off device, and P-type GaN-based mesas are used to form the gate, which depletes the two-dimensional electron gas in the channel. If we move over to the analog circuitry area of the chip, here we see one of the analog transistors. It looks like a conventional MOSFET with a source and drain and a gate in between. And here we show a SEM image of the layout, and you can see we have analog circuitry laid out on the surface of the chip. TechInsights has done some circuit extraction on some of these kinds of devices. So the next one, this is what we call a reversal. We actually procured some more samples of the Aukey PAU 50 24-watt chargers a little bit later on in April 2019. And to our surprise, we found that this time, rather than the Navitas chip, it contained a Power Integrations offline CVCC QR flyback switcher switch, which is designed for 650 volts and is based on silicon. So we're not really sure why Aukey switched back to silicon technology, but they did. There was a slight difference in the markings, but otherwise the devices seem to be identical. So continuing our story about the devices that we have analyzed, this is the Anchor PowerPort Atom 1 charger, which we procured also in March 2019. And here, for the first time, we found a Power Integrations PowiGaN device. So this is Power Integrations GaN-based technology. So here's the device. It has a power density of 8.3 watts per inch cube, which we'll talk a little bit more about later. And here's an X-ray showing that there's a GaN-based die and three silicon-based die. The GaN die is wired up in a cascode configuration. But gallium nitride is not always winning. And here's an example which I've called Silicon Strikes Back, which is the Energy 60C USB-C 60-watt charger. TechInsights procured this product, which is made by Delta Products Group, in April 2019. And we were rather expecting to see gallium nitride in this, but we found it actually contains an Infineon 600-volt superjunction CoolMOS technology chip or switch. But they have achieved quite high power density, 17.9 watts per inch cube, which was the highest power density we had seen at the time. Curiously, the manufacturer chose to obscure the Infineon CoolMOS markings with paint, which we had to remove to identify the chip. And here's a photograph of the die, and we have in fact done full analysis on this Infineon superjunction CoolMOS device. So the first few charges we've seen were made by aftermarket suppliers hoping to sell into the aftermarket market for USB chargers. This is the first one where we saw GaN in a OEM device. So the Oppo Reno Ace comes with a 65-watt charger with this part number, and we found that it contained the Power Integrations PowiGaN technology, which, as I mentioned, integrates a normally on GaN hemped into a cascode configuration with gate control circuitry into a single package. Slightly different than the one that we found previously. So a little bit about the Power Integrations GaN technology. So it is actually quite different from what Navitas is doing and the other vendors. Perhaps the most interesting thing is rather than GaN on silicon, which is the normal approach being taken by most power electronics vendors, they're using GaN on sapphire, fairly large transistors with a 74 micron drain pitch, and we have a full analysis of this chip available. Here we calculate the percentage of the die used by the active transistor, which is 75%. So again, GaN on sapphire process, which we've considered to be a little bit unusual since it's higher. So looking at another design win, this one is Navitas, where they scored a design win in the Xiaomi Tech AD65G. And we found that it contained two Navitas devices, the 6117 and the 6115. The key thing about this OEM device from Xiaomi Tech is that it achieves the 20 watts per cubic inch target for power density. One last device to discuss before we wrap up. There is a new entrant from China. So this Dongwu Huang Electronics makes a USB charger, actually with several different brandings. We purchased a couple of ones, and we found that it contains the Innoscience, which is a Chinese manufacturer, IN650D02, 650 volt GaN power HEMT. We do at the present time in our lab on this technology, and we found it's based on a 4-metal GaN on silicon process. And here we show a cross-sectional overview of the device structure. And then a very nice die photograph here. Just backing up, just to give a reference device, Apple and Samsung are, of course, been making USB chargers for their mobile devices for many, many years. This is Apple's USB-C charger. It has a pretty low power density, 5.9 watts per cubic inch. It's quite small, of course. We are expecting that both Apple and Samsung will release 65 watt chargers based on GaN in the near future. But we have not seen them yet, but we're watching for them. So finally, as we wrap up, this shows the trend in power density for USB-C chargers. You can see that as time goes on, the power density is being increasing. Here's the Xiaomi Tech, which achieves the 20 watts per cubic inch. We expect other OEMs to follow, Samsung and Apple, and I'm sure they will produce market-leading devices. So, by way of a few concluding remarks, the USB-C fast charger market is a rapid area of rapid innovation in the consumer electronics market. It's probably going to be the first mass market application for GaN-based technology, and we anticipate the major OEMs will be releasing GaN-based chargers in the near future, the next 12 months or so. Xiaomi is the first company to achieve the 20 watts per cubic inch target. At the present time, this emerging market is dominated by 3 players, Navitas, Power Integrations, and Innoscience. However, ST Microelectronics is making an aggressive play in this market with their new master GaN technology, which we are presently analyzing. The USB-C charger market, which is smaller than the full charger market, is expected to grow by about 25% in the next few years, starting from a base of 400 million-ish in 2018, based on data from Credence Research. Here's a few references and links which we can send to blogs and articles we've written, and thank you very much for listening.